Hi everyone, I'm Zhen Xie, a postdoctor in University of California, Merced. In this talk, I will present a paper, Mobilization-based molecular dynamic simulations on big memory system. This is a joint work with my fellow students and my advisor, Professor Dong Li. I will introduce the background. The high-density, byte-addressable low-volatile memory, NVM, is promising for implementation large capacity big memory. For instance, the recent Intel OptDC persistent memory could support up to 9 GB memory capacity on a single machine. Based on that, some cloud service, such as Amazon Web Service, released the DRAM-based high memory instance, which can provide up to 24 GB memory on an 8 sockets machine. For the molecular dynamic simulation, it can be considered compute-bound, where the limitation step is how much compute performance they can provide over time. Usually, more than 90% of execution time is spent on computation, and MD consumes small memory even for a large-scale simulation. For example, the cyclical simulation for 1 million particles consumes only 3.6 GB memory, which is far less than the typical memory capacity in a node. The traditional performance optimization on MD focuses on increasing the parallelisms, such performance optimization is bounded by processors' theoretical peak performance, not for memory utilization. First, we will give some background of MD. MD is a fundamental method for modeling examples of particles. It is a common and general computational method and gives scientists the ability to track the movements of particles. It computes the interaction between a collision of particles and play important role in weather field. By performing MD simulation, these systems and the properties can be obtained more easily compared with experiments. And MD is typically compute-bound, not bounded by memory bandwidth or capacity. This is the workflow of MD. MD usually involves a large number of particles. It computes energies and force between particles based on the computation of interparticle potentials. The calculation of potentials domains the simulation time at least 90% of the total time. Besides, this calculation is based on data structure of a few bytes to present particles, consuming small memory even for a large-scale simulation. So for the most time-consuming part of MD, the computation of automatic force on each particle is determined by the type of potential functions and the distance between an atom and its labels. And the cutoff distance is usually used to limit the pairwise computation only to label particles. Therefore, if different pairs has some distance, the computation of potential is the same. However, in direct numerical simulation, such computation will be repeated. For the most time-consuming part of MD, the computation of inter-automatic force on each particle is determined by the type of potential functions and the distance between an atom and its labels. And the cutoff instance is usually used to limit the pairwise computation only to label particles. Therefore, if the pair has the same distance, the computation of potentials is the same. However, in direct numerical simulation, such a computation will be repeated. So to reduce the computation cost, lookup tables are often used to reduce the repeated computation of potentials. For instance, pairwise lookup table uses the distance between a pair of particles as the key and save the potentials as the value. However, one table lookup may replace one potential computation. And we also have some challenge to use this method. The first challenge is how to efficiently. So we also have some challenges for using this method. The first challenge is how to handle operations for lookup table. The memory accesses are dominated by writes in the beginning of the MD simulation in order to populate the lookup table. Once the lookup table is populated, the memory access are dominated by reads in the remaining of the MD simulation. The common data structure to build the lookup table, such as B plus tree and the LM tree, can provide high performance for neither read and write, but not for both. Hence, they lack the flexibility to accommodate the variance of the memory access pattern to the lookup table in the MD simulation. So the second challenge is due to random accesses in lookup table and the latency to memory. The calculation of pairwise potential for SW application is almost the same to the memory read latency. So the pairwise lookup table only bring limited performance benefits. To ensure the performance benefit of using lookup table, the memory access latency to use the lookup table must be smaller than the calculation of a potential to be replaced here. And the third challenge is if we visualize the position of particles in the subgrid, they form a shape. One shape could be a result of a translational movement from another shape, and then they have the same potentials because the distance between particles remain unchanged. Rotation changes the order of replacement between particles, and the scaling movements change the distance. So the pattern recognition should distinguish rotation and scaling as different patterns. The required algorithm need to be translation invariant, but rotation and scaling sensitive. So in this paper, we propose our solution. It includes a new data structure to build the new lookup table and a subgrid-based replacement structures. And it can also capture the patterns in subgrid based on the image recognition algorithms. So I will introduce them in details. The first one is lookup table design. We extend the LS tree to two-phase LSM tree. Two-phase LSM tree is hybrid two-phase distinct in read and write intensity. At the beginning of the simulation, the lookup table is almost empty. So the two-phase LSM tree reuse the data layout and the implementations in the original LSM tree design. As the simulation progresses, the lookup table contains more entries so that lookup table are more likely to hit in the table. The phase is as a read dominated. We compact the multiple level SST field in NVM to a one level structure of data blocks in NVM. Based on this design, we can significantly reduce read amplifications and the latency of read operations. The second optimization is, in this paper, we introduce a new memoization approach to accelerate MD. In particular, we partition the computation field in empty simulation into multiple subgrid and replace all pairwise computation in a subgrid as a whole. This brings much larger performance improvement than the traditional pairwise approach. So based on this method, we have a large number of patterns, and each of which defines a number of particles in a subgrid and the pairwise distance between particles. So we can use pattern to build new lookup table for higher performance. And at the runtime, the lookup table need to deploy a pattern matching algorithm to repeatedly extract the features of a subgrid and recognize it as the pattern to search for the matched subgrid in the lookup table. So as we can see from this figure, we can extract the feature from two figures. Each set of features contains sufficient information of this picture. Then we can compare the features to get the similarity of two pictures, which is more easy to compute. So we propose a new algorithm, the lookup moment algorithm. The basic idea is we use the advantages of two previous two algorithms and combine them to build a new moment algorithm. Based on that, it can extract rich features and keep invariance for translation, but sensitive for rotation and scanning. We evaluated the effectiveness of the proposed lookup table moments by collecting 400,000 subgrid from 9 MD simulations. And the result can support our design. We can see from this figure, the figure A presents the 7 moments after translational moments. All moments remain stable when the translational moments are applied, which indicating the lookup table moments are translation invariant. The figure B to C shows that the first 4 moments increases as the angle of rotation and the factor of scanning increases. Therefore, the lookup moments are sensitive to rotation and scanning moments. We evaluated MD to HM on a server equipped with 2 Intel Xeon processors. Each socket has 12 DIMM slots. In total, the system has 192 gigabytes DRAM and 1.5 gigabytes NVM. We configured the OpenDC to application direct mode for maximum control. We used 9 MD problems that cover a wide range of applications and come from NAMS benchmarks. MD to HM is implemented based on NAMS, which is the state-of-the-art MD simulation package, and will compare it with the LSM tree-based key-value store, RocksDB, which is a state-of-the-art key-value store system. Overall, the MD to HM outperforms the baseline numerical framework on all the input problems by up to 9.7 times and 7.6 times speedup on average. MD to HM with two-phase LSM tree outperforms the RocksDB key-value store system by an average speedup of 2.7 times. We highlight that the computation part of MD with two-phase LSM tree can achieve higher performance, and the average speedup is almost 28 times. We also evaluated the effectiveness of lookup table. The subgrid lookup table is expected to capture most subgrid patterns in a simulation as the simulation advanced. For example, the hit rate on the lookup table increases throughout a simulation. For a result, the lookup table reaches over 90% hit rate in 50,000 time steps for all problems. We report the breakdown of these overhead in line simulation in the figure. 5 components contribute most overhead of HD to HM framework, namely moments calculation, retrieval in memory table, retrieval in index tree, retrieval in data block, and the potentials transfer. Among them, moment calculation comes from the subgrid pattern recognition algorithm. The potential transfer comes from the computation replacement structure, and the others comes from the two-phase LSM tree data structure. Indexing search usually take a large portion of total execution time, and the pattern recognition is usually not that expensive. Okay, in conclusion, the big memory works as an untraditional accelerator to greatly improve performance of FD simulation. And the memoization techniques plays an important role to make a big memory useful for MD simulation, but it has some challenges need to be resolved, such like this paper. So our framework MD2PM leads to an average speed up of 7.6 times over the traditional simulation method for MD simulation without losing the simulation quality. Okay, I'm done with this talk. Thanks everyone. I'm ready to take any questions.